Hey, here's a few lectures on confidence intervals and a closely related idea of hypothesis testing. So some of these I'd like you to try out in the latest case. This first page here is more of a background story, but let me run through it quickly. So one thing, usually we start with, we have an interest in a broad population, whether that's truly, say, a national population, but it can be much smaller. Maybe we're interested in the Asbury student body, but we don't have the time or money or inclination to talk to all 1,400 students, especially if it's a in-depth survey or interview. So we take a sample from that. Again, it has to, from the sampling lectures, it's got to be random. Everyone that's in the population has to have an equally likely chance of being represented in the sample. Okay, so let me run through these steps here. So we're interested in something broader. This bigger population mean is usually what we're interested in, but we don't have the time or money to ask everyone. So we take a sample of size n, and that's sometimes to be determined depending on how accurate we want to be, or maybe our resources. And depending on the type of variable, maybe it's a proportion, the percentage of college students that finish in 4 years, or could be an average, their average GPA, or their average weight, or their average calories per day. Because it's a sample, even though everyone has an equally likely chance, different samples are going to be at least a little bit different, or typically a little bit, or maybe quite a bit different if it's a small sample. And the question is then, how much will they differ? Well, there's this big idea, kind of a technical term, but in statistics, the central limit theorem. So you can impress people when they ask you what you're studying in your class, and you could say, oh, the central limit theorem. Okay, so then I don't know if they'll be impressed or not. Probably not. So anyway, so this, as you can see here, it says no matter what the distribution of the population data, even if it's not normal, it could be bimodal, it could be heavily skewed one way or with outliers. Whatever the distribution is of the actual population, the distribution of the sample means, which is kind of a strange idea because we're only going to find one sample, but if we did take several hundreds, say, of samples and plotted their means, then that would look like a nice bell-shaped normal curve. So we have this concept. It sounds, in some ways it plays the same role or has some analogies to the standard deviation, but it's actually called the standard error. So for proportions, the standard error is the square root of the proportion times 1 minus proportion divided by the square root of n. And if it's not a proportion, if it's continuous data like GPA or height or whatever, then the standard error is the standard deviation divided by the square root of n. And we'll see some examples here in the next few pages. So one of the two main things from this series here is finding confidence intervals. And typically, we want a pretty high degree of confidence. You say, well, how about 100%? Well, statistically, that would be really wide. We can't, if I wanted to guess 100% guarantee what your salary is going to be here, it could be anywhere from 0 or even negative 100,000 if you had lost some big lawsuit, up to 1,000,000. But even that wouldn't be 100%. Possibly you could win the lottery, or you could sign some huge contract to sell your company to Google for millions, and I'd be wrong. So there are some limits there, and that's where we try to trade off. Most typically it's going to be this one here, the 95%. Okay, that didn't come out very well. Try that. Okay, that's not much better. Okay. All right, just there we go. Anyway, the idea here, we use the sample value. So sample proportion is p hat, or the sample average x bar. And then depending on how wide we want, we have these. You'll recognize this is the same z from the normal distribution. So just to focus on the main one, or the most popular one, 95% confidence. is the sample average plus or minus just under 2, 1.96 standard errors. Okay. Let me illustrate that with a couple examples. So proportion, yeah, you might have proportion, percentage of people in your survey that are what have some quality, percentage male, percentage that accomplish something or what have you. So here we're not given the raw data, but we find the sample proportion is 60%, the sample size is 100, and from that we want to infer, well, what confidence do we have around that 60%? So 60.60 is the point estimate, but then around that we want to have a range. So normally you wouldn't do 5 or 6 like I've done here, confidence intervals. You just do 1, but this illustrates as well, if to be 68% confident, that's roughly between 55 and 65%. If we want to go out to, let's just jump down to 95%, plugging in, again, this higher z-value, everything else is the same in this problem, then it's almost plus or minus, not quite 10%, but I'll exaggerate a little bit. It's kind of between 50 and 70%. So again, we'd say, well, that's good that we can be 95% confident, but then, if this election, we're starting to say, well, on the low end, we could be wrong, which does happen sometimes. And then to be 99% confidence interval, it's almost a range of 29%. So the second example is identical with now, though, what if we were looking at samples of size 900? And in this case, the standard error is much smaller. We're dividing by the square root of 900, which is 30. So now, for example, I don't have it all worked out here, but 95% confidence interval would be about plus or minus 3% versus, what was it up here? Almost 10%. So you can say, well, why don't we ask 900 people? Well, you gotta survey 900 people or collect information, which in some cases may be easy if it's an automated thing or a one question, but if it's an hour-long survey, some big psychology study or economic interviewing, 900 businesses on their finances, well, that would be quite costly. Okay. The third example is, whoa, and again, you get a taste of my handwriting here, so this actually isn't too bad other than some scribble, but anyway. The last one kind of flips it around and says, well, what if we come in predetermined, we want to have a certain margin of error before we do our study? What would be the, how many people would we have to sample, or how many businesses or whatever we're interested in? So here it's a very, up here it was, plus or minus, 3% is usually pretty typical for like election results, if you see that. So if we want to go down to 0.5%, we plug that into our formula. We leave n, I'll try my highlighting again, not so great, but that's nothing. Okay. N is the unknown, what we're solving for to hit this certain confidence, very tight range. And then the rest is algebra, which I guess I messed up at some point, and then I redid. So here, if we did that, yeah, we need almost 37,000 observations. So that's, again, maybe in the rare case, you might be, all right, we can do that if we were maybe in a factory where there's a high production rate. You have a tech digital reader or something that can sample that much. If you're going to do that, though, you might as well just sample everything. So the point here being, yeah, I mean, usually between going from 30 to 100 to maybe a few hundred, you get a lot of pretty good returns in terms of the confidence range. Beyond that, though, if you want a very, very tight prediction, then you got to go up into tens of thousands or higher.